Hello guys, let me try to give a very brief explanation of what a quotient category is. Suppose you have a category, let's call it C, and on this category you have an equivalence relation, and this is a special equivalence relation called a congruence, and it is special in the following way. First of all, this is an equivalence relation on the set of home sets, where the home sets are, of course, home sets of pairs AB with objects AB in the category. And this equivalence relation satisfies two additional axioms. The first one being that if F, which is an element of some home set, is equivalent to another element, let's call it G, then F and G must lie in the same home set. So this means that if you are to have two elements that are equivalent, they need to lie in the home set of the same pair of elements or objects of your category. This is the first thing. And the second thing is if your F is equivalent to another element of the home set, which we might call F bar, and the same for G. G is equivalent to G bar. And if you can combine F with G, compose F with G, then you must have that F composed with G is equivalent to F bar composed G bar. So these are just the axioms for a congruence. And now using this congruence we have by assumption in our category C, we can establish a new category, and this new category is the quotient category, which I call C bracket, but this is not standard notation. You may, of course, use your own. So what are the objects in C bracket? You just keep your objects from your category C, so nothing happens there. And the morphisms in C bracket, in the quotient category, are equivalence classes under this congruence of morphisms in C. And of course, we need to verify that this satisfies the axioms for a category. Well, first of all, note that the composition of equivalence classes in C bracket is well defined, precisely because we have a congruence such that F equivalent to F bar and G equivalent to G bar satisfies F G equivalent to F bar G bar. So you can define the composition of the equivalence class of F with the equivalence class of G as the equivalence class of F composed with G. And this is by this second property of the congruence, the same as the equivalence class of F bar composed with G bar. So this covers the well-definedness, and the rest is standard. Of course, you have associativity of the composition because you have it in your category C, and you have identity elements because you have it in your category C, and nothing happens to them. So This is, in brief, the definition of a quotient category. And if you like, I would proceed to show you an example of a quotient category in the next tutorial. And this example will be the category H-top, which plays an important role in algebraic topology. So, if you like, see you in the next tutorial. Thank you for watching.